Welcome to Kitchen Table Electronics Lesson 4.2, where we measure more non-linear devices using our ramp generator code, ramp generator, and our plotting code. So here we go. What are we going to do? We are going to measure the Zener Diode, the bipolar transistor, and the field effect transistor. All of these will require some modifications to our ramp plotting hardware and our code for plotting the data, but I will show you how to do this. They're all pretty straightforward. Let's start though with our diode plotter unmodified. So we're going to do the same thing now. We're going to take a 1 kilo ohm resistor, in this case not a 10 kilo ohm resistor, we're using a smaller resistor here, and we're going to connect a Zener diode as our device under test. Here is the symbol for a Zener diode, anode and cathode, and you'll notice now we're using the Zener diode in reverse bias. Remember, this is the direction of positive current flow for a diode, and now we're going to make this go from 0 to plus 5 volts. What's going to happen here? Well, a Zener diode is actually designed to have a reverse breakdown voltage that is reasonably reproducible, and so it acts as a source of constant voltage, providing you run enough current through it. We're not really going to do this simply because 1 kilo ohm is not really a small enough resistor. One would use a much smaller resistor for a real Zener diode supply. I just don't want to drag too much current out of my Arduino with all the other things I've got loaded up onto it. So I'm going to cheat and use a somewhat bigger resistor and get a somewhat poorer Zener response. Once again, the Zener diode used in reverse bias and will break down in reverse bias. And if one has a small enough resistor, you can look at a Zener diode data sheet. It will give you an essentially constant value of voltage as you put different loads on the diode. Okay, so other than changing to a 1 kilo ohm resistor, there's nothing much to do. When we now run our ramp generator program on this circuit, you'll see that the output looks quite different. Instead of being the straight line it was for the regular diode in reverse, because the diode never drew any current over the voltage range, the Zener starts drawing current here, and so the measured voltage starts dropping as the ramp voltage increases above some critical amount. Okay, we saved the file. We now load it up into our curve plotter, and I tell the curve plotter, by the way, that the current sensing resistor is 1 kilo ohm, so the currents here look larger than they did for the diode. And you can see here we're going all the way now up to about a couple of volts before significant currents start to flow. And if we really let this thing rip, we'd eventually flatten out here at 3.3 volts. But once again, I didn't want to do that. So there's the Zener diode. Let's look at a much more interesting device here, which is the bipolar transistor. The bipolar transistor actually looks like a pair of diodes back to back. So here's N-doped silicon full of electrons, P-doped silicon full of holes. And so this then would look like a regular diode. And this way around, the arrow would look as though it was going this way. This would be what would make the current flow. The electrons went this way. But, oh, wait a minute, I've got that wrong. Okay. Let's have a look. This is the P side, this is the N side. And so if we make this positive, that's right, current is going to flow around this way. So this looks like the anode of the diode. This now is another piece of N-type silicon wedged up against this P-type silicon. So this now, if this is made positive, is reverse biased, opposite bias to this diode here. And so no current at all can flow here. The secret to transistor action is that if this central P region is made very, very thin indeed, then current flowing through this diode can make a current flow through this diode, even although it is reversed biased. This is the transistor action discovered at Bell Labs, and which of course led to the invention of the transistor. This middle part is called the base, this bottom part the emitter, and this top part the collector. Here's a symbol here for an NPN transistor, NPN, where the base is made of P-type semiconductor. And here's the arrow showing the direction of positive current flow. It's also quite possible and regularly done to make transistors from PNP type material, and then one uses them back to front. This part then gets connected to the plus 5 volt supply rather than ground. Okay, we're going to use a 2N3904 standard NPN transistor. The data sheet is on the website, so you can download that and take a look at it. You'll see that the connections go, one is the emitter to the base through the collector. So if you hold the case looking at the flat side, which will have the 2N3904 printed on it, we go emitter, base, collector. Okay, I've extracted some of the data sheet here, and you see it's got data for a whole series of transistors in this range, some of them NPN, some of them PNP. But here is the 3904. It lists a quantity called the DC current gain. Let's just go back to this picture here. When you overcome the thermal barrier here to conduction of this junction by applying an adequate bias, something greater than ½ volt between the base and the emitter, then current can freely move from the base to the emitter. But having demolished the thermal barrier now, electrons are free to diffuse into this region here, and where they feel the huge electric field from this reverse bias junction here. And so if this transistor is designed well, most of these electrons are just swept up by the collector, which is why it's called a collector. The only way that base current flows is if some of these electrons recombine with holes, and so a very small base current can correspond to a very large current between the emitter and collector. The ratio of these two is called the DC current gain, and it's given the parameter value HFE. So the DC current gain depends on the voltage across the collector and emitter and the current. So here it is 1 volt between the collector and the emitter at 1 milliamp DC, and for the 3904 you can see 70 is typical. To give you some feeling of how these varies, at 10 milliamps DC, the 3904 has a typical gain of about 100, but can have a maximum of 300. So HFE is a parameter that varies a lot from one transistor to the next. There's another parameter here. When we look at the IV curve, we'll see that as we turn the transistor on, we get to, as we make current go through here, we get to almost 0 volts between the collector and emitter, but not quite. And this is VCE, the saturation voltage, when you're driving the base hard. And here it is, it's 0.2 or 0.3 of a volt, depending on the conditions. And then finally, this is this base emitter saturation voltage. When you're turning the transistor on, it's about 0.7 of a volt, so it's like a diode turned on in this direction, and it can be as high as nearly a volt in appropriate conditions. Okay, let's make a transistor tester circuit. So now we're going to need an extra resistor. We want a current sensing resistor in the collector because we're going to measure the current through the collector lead of the diode. So here we go, plus 5 volts goes to the collector through a 10 kilo ohm resistor, or 1 kilo ohm resistor, I'm sorry. This, by the way, the nice thing about these Fritzing diagrams is they show you your color codes. The base is driven by the ramp generator here through a 10 kilo ohm resistor, here it is, and then the emitter is grounded. So here's our circuit, here's what my real life circuit looked like. I took the collector here to the analog read on the Arduino. This was the pin 3 or ramp generator from the op-amp, which was driven by pin 3 on the Arduino. So this is the DC ramp from my op-amp converter, and that's driving this 10 kilo ohm base resistor here. You can't see it because this lead curves down and plugs into the board about here. Okay, so you're going to make that circuit up, and we're going to change our curve plotter. Our ramp generator's fine. Our curve plotter we're going to change, and we're going to change it because what we're doing now is a little different. We are measuring the voltage at this point here. The voltage at this point is not driven by the ramp anymore. It's held constant at whatever the Arduino maximum voltage is. So now the current through this resistor will be given by this voltage, which in my case is actually 4.91, minus the red voltage. And so that will now tell me the voltage across this resistor divided by 1K will give me the current through it. And then the current into the base is going to be the forward bias of this diode here, will be the value of voltage at this point when this transistor turns on. That was this VBE. And take that away from the input ramp, divide by 10 kilo ohms, and you have the input current. So we're going to plot current through the collector against input current. Okay, so we now need to convert the applied voltage into a base current. How do we do this? So here we have a little loop. We have an array here, V applied, or rather a base current array, which here we made an array of list length full of zeros. So now we're going to fill this array with this little for loop here for IN range list length. And so the applied voltage, once again, is whatever the maximum is times this index divided by list length, the same as calculated before. However, if the applied voltage calculated is less than 0.6 volts, the base current isn't going to be anything because the diode is not turned on yet. That's the base emitter diode. Otherwise, once we exceed 0.6 volts, and you'll see that this is actually an approximation because the diode doesn't suddenly turn on, as you know, and this turn on voltage will depend a bit on the device you're using and all the rest of it. But never mind, we're making life simple here and we're going to use this approximation. So we're going to fill this with zeros till V applied gets to 0.6 volts. Once we exceed 0.6 volts, we're then going to take V applied minus 0.6. That is the voltage across this base resistor here. And we are going to divide it by the current sensor, which in this case is 10 kilo ohms. So when you run the range program, enter 10 kilo ohms here. And then we have our base current. Okay, now we're going to plot the, I said earlier we're going to plot the collector current. I didn't put that extra resistor value in. So we are going to plot actually the base current and we're going to plot the measured voltage across the collector emitter junction as our output variable on an XY plot. And the rest is code as per before. So here we go. Now, because the collector emitter voltage goes all the way up to 5 volts, and I was using code based on a ramp generator earlier, whereas we now have a voltage that starts at 5 volts, my X range isn't right, but you know what? I didn't want to mess with my code. Feel free to do that if you want to. You can still see that the program is working from the fact that as you turn the transistor on, as you increment the ramp here, the voltage between the collector and emitter comes crashing down as you start drawing current through that collector resistor. So here's the raw data, and your raw data will look something like this. If you use my code, you might get nice about limits on the graph if you want to. Here is what the output looks like. So here's the voltage between the collector and the emitter. It starts at 5 volts because the transistor is not taking any current. As you start to turn on the transistor, you take more current through the collector, the voltage falls precipitously, and then eventually the transistor is turned on as hard as it can be. This then is that VCE sat, so this is the residual voltage between the collector and the emitter right here, you see this doesn't actually go to 0. Now this curve illustrates a lot of things about transistors. You probably think of transistors as amplifiers, and they certainly are, and we're going to use one as an amplifier. If you want to use this as an amplifier, you obviously want to be in this range here, where the voltage between the collector and emitter can change to give you an output signal. However, if you just want to drive something, so let's say you've got an output from your Arduino, which is a limited number of milliamps, and you want to light a lamp or switch a heavy-duty relay, then you will take the output of your Arduino, connect it to the base of a transistor, connect your load in series with the collector, make sure that the HFE of the transistor is enough such that when your Arduino is at logic 1, you can drive the current you want through the collector, because the ratio of the two is HFE, and then you want to operate in this saturated region here. It's very bad to design a switch to sit somewhere here. The reason is that you have maximum power dissipation somewhere in here where the voltage across the transistor is largest for a given current. Here the current's a lot higher, but the voltage across the transistor is tiny, so the power dissipated by the transistor is small. It makes a great switch. Here it's an amplifier, but you could exceed the power dissipation of the transistor if you put enough load across it. Anyway, we'll take a greater look at that later on. Now I can take my cursor and I can measure at the end of this linear region here what the current through the transistor is by measuring the voltage dropped here, and then knowing I had a 1K resistor. So at this point, I see that I've got 0.05 milliamps base current. VCE is apparently 0.28 volts. That's what my cursor reported. So the voltage across the resistor then is the collector voltage of 0.28 volts, taken away from that 4.91 volts, which was the positive supply, divided by the 1 kilo ohm. Remember, the collector resistor was 1K, not 10K, and that gave me 4.63 milliamps. 4.63 milliamps divided by 0.05 milliamps is 93. So my HFE is about 100, and that squares with the data sheet. Okay, what is HFE for your transistor? You're going to measure this at home on your kitchen table. However, a mystery emerges. Clearly, HFE is very variable. How could you hold a transistor reliably in this area if you wanted to make an amplifier? That's the subject of the next class.